The last integration technique that I would like to discuss is called substitution, and some material on this technique can be found in section 5.6 of the book. We have a number of problems that have similar features. So the problem is that we wish to calculate the primitive of the following functions. The first one is sine of x squared multiplied by x. The second is that we wish to calculate the primitive of the function e to the minus square root of x divided by 2 square root of x. The third one is the function cosine of x divided by sine of x. The fourth is the question how to compute the primitive of the function g prime of x over g of x, where gx is some unspecified function. And the fifth one is a similar question, namely to compute the primitive of the function gx to the power n minus 1 multiplied by its derivative. And here, to differentiate from the fourth problem, we have to require n not to be equal to 0. So again, of course, g of x should have some nice form. It should be differentiable. Okay, now the question is what these problems have in common, and we will see this in a minute. Okay, now let's look at the first integral. So what you can see is that if we wish to have an explicit form for the primitive, is that it should contain some term with cosine of x squared. So let us compute the derivative of that function. And what you miraculously see is that the derivative of this function cosine of x squared is equal to minus sine of the same argument x squared multiplied by 2x by virtue of the chain rule. So this means that if we want to know the primitive, that the primitive of this function is equal to cosine of x squared. So, and since minus sine of x squared multiplied by 2x differs a factor minus 2 from the function on the left side that we wish to integrate, we can see that the required primitive is just, we have to compensate for this extra factor minus 2 by dividing it out, and so we get minus cosine x squared. Now let's look at the second integral. Of course, essentially, primitive should contain a factor which has e to the minus square root of x in it. So let's compute the derivative of that one, and then we get the same function e to the minus square root of x multiplied by minus 1 over 2 square root of x, which is the derivative of this power by virtue of the chain rule. And then again we can give the primitive very easily, because what you see is that this derivative differs a term minus 1 with the required function that we wish to integrate. So we have to compensate by multiplying by minus 1, and we get minus e to the minus square root of x as the primitive. And because of we differentiate it again, we get precisely this function back. Now, the primitive of the function cosine of x divided by sine of x is a little bit more complicated, but what we see is that this quotient is nothing but cosine of x multiplied by 1 over sine of x. So 1 over a function of x, and essentially this the primitive should contain the primitive of the function 1 over u, which is a natural logarithm of u. So we get a natural logarithm of sine of x, and if we differentiate it, you have to distinguish the cases where sine of x is positive and sine of x is negative. But if you compute the derivative by the chain rule, you will get cosine of x divided by sine of x. Of course, provided that x is not equal to 0, because then sine of x is equal to 0. Or in fact, we cannot take any value of x where sine of x equals 0. Okay, and so what we get as the required primitive is the natural logarithm of sine of x plus a constant. Of course, this primitive only is true whenever sine of x is not equal to 0. Now, the third integral is, of course, a special case of the fourth one, where we take g of x equal to sine of x. So you get a similar form, namely the logarithm of the absolute value of the function g of x. And if you differentiate and distinguish the cases where g of x is positive and g of x is negative, then we get the same thing. It's g prime of x, the derivative, divided by g of x. And then again, the required integral is equal to the natural logarithm of this function g of x in absolute value. Now the fifth one, of course, if we look at the primitive of the function g of x to the power n minus 1 multiplied by the derivative, it should contain a term g of x to the power n, because integrating makes one have to raise the power by 1. So if we do so and we compute the derivative of what we get, then we get n times g of x to the power n minus 1. By differentiating decreases the power by 1, but by the chain rule we have to multiply by the derivative of this function. And we see that we have a factor of n between what we have to integrate over here and between this derivative. So our required primitive is then equal to 1 over n of multiplied by gx to the power n. Now what do these problems have in common is that essentially what we wished to integrate was a function little f of a function h of x multiplied by the derivative of that function h of x. Yeah, so in case 1, our function little f is the sinus function, and h of x is x squared. In the second case, the function little f was e to the minus x, and our function h of x is square root of x. The third one, little f, is equal to 1 over the argument, 1 over x, and our function h of x is sine of x. And the fourth case is our functions little f were 1 over the argument, and in the last one it was the n minus 1th power of the argument. And what we see here is that the primitive is equal then to the primitive of this function little f evaluated in point h of x.